Most of the AI we hear about, it's really good at one thing, prediction. It sees a pattern, and it guesses what's going to happen next. But what if? What if we had an AI that could go a step deeper? An AI that could understand not just what happens, but why it happens. That is a whole different ballgame. So let's dive in.
I mean, it sounds simple, right? We humans do this kind of thing all the time. But for a computer, oh man, telling the difference between two things just happening at the same time, that's correlation. And one thing actually causing another? Well, that's one of the toughest nuts to crack in all of artificial intelligence.
And get this, here's the really frustrating part. Even when we do manage to build a model that can figure out causality for one specific problem, the moment you get new data, even if it's just a little bit different, you have to toss the whole thing out. Yep, start completely from scratch, every single time.
Researchers have a name for this whole mess. They call it the retraining trap. And it's exactly what it sounds like. It's this never-ending, super inefficient cycle of building, training, and then rebuilding a model for every single new question you have. It's slow, it's expensive, and frankly, it's a huge roadblock to progress.
Now, the whole field dedicated to solving this is called causal inference, and it's all about tackling those really, really important what-if questions. Like what if a doctor gives a patient this drug instead of that one? Or what if a government changes a major economic policy? We're talking about questions where the answers have huge, real-world consequences.
Okay, so this really puts it in black and white, right? The old way versus where we want to be. On one hand, you've got the current grind. New data comes in, you build a whole new model, and you wait for hours, maybe even days for it to train. Ugh. But the dream is to have one single, powerful model that's already trained up. You just hand it a new data set, and boom, you get your answers in seconds.
So how do we get there? Well, it's pretty clear we can't just make tiny little adjustments to the old way of doing things. That's just not going to cut it. We need a complete fundamental shift in our thinking, a totally new paradigm for AI.
And you know what? We've actually seen this kind of massive shift happen before. Just think about it. Foundation models have totally revolutionized how we deal with language. I'm talking about models like ChatGPT. It wasn't trained on just one book or one article. No way. It was trained on this colossal chunk of the internet to learn the deep underlying rules of language itself.
And that's the key takeaway right there. A foundation model gets pre-trained on just a mind-boggling amount of data. It learns the fundamentals so well that you can then adapt it to all sorts of different tasks without ever having to go back to square one.
Okay, so this all leads to the big kind of billion-dollar question, right? Learning language is one thing, and it's amazing. But can we actually do the same thing for causality? Can we build a foundation model that learns the deep, abstract principles of cause and effect?
Well, a team of researchers from LMU Munich thinks the answer is a big yes, and they put forward a framework to do just that. They call it CausalFM.
So let's be clear. CausalFM isn't just another small improvement. It's designed from the ground up to be a true foundation model, but for causality. The whole idea is one model, you train it once, and then it can handle a whole bunch of different causal problems.
So what's the secret sauce here? How does it work? Well, under the hood, it's using a special kind of tech called a prior data fitted network, or a PFN for short. Now, here's a good way to think about it. Instead of learning by playing just one real game, a PFN is more like an athlete who's run through millions of different practice drills in a hyper-realistic simulator. It learns the fundamental physics of the game long before it ever steps onto the actual field.
Okay, so if it's learning from a simulator, what do those practice drills for causality even look like? How do you create millions of them? The answer is pretty cool. You build millions of tiny, self-contained, simulated worlds, and each one has its own unique rulebook for how cause and effect works inside it.
And these rulebooks have a technical name. They're called Structural Causal Models, or SCMs. Just think of each SCM as a simple blueprint. It lays out the basic laws of physics for that one little world. It'll say things like, okay, in this world, A always causes B, or C has absolutely nothing to do with A, and so on.
The way they train this thing is actually pretty fascinating. It's basically a three-step process. First, the system just generates millions of these unique SCM blueprints. Then, for each of those blueprints, it creates a bunch of fake or synthetic data that perfectly follows those rules. And finally, step 3, it gives CausalFM a single job. Look at this pile of synthetic data and figure out the true causal effect that we already know is there. And it does this again and again and again, literally millions of times.
Now, this is a really important point to remember.
The model isn't just making up causal relationships out of thin air. That would be dangerous. A human expert, a doctor, an economist, still has to lay out the basic map of the problem based on what they know about their field. The human provides the causal map, and then the model does all the heavy lifting, all the complex math.
All right, so the theory sounds amazing, right? But does it actually work in practice? Let's take a look at the results. How did CausalFM stack up when they put it head-to-head with the current state-of-the-art methods?
Okay, so they ran it through a whole bunch of benchmark tests, and what they found was that CausalFM's performance was right up there with all the top dogs, methods like S-Learner, T-Learner, you name it. So in terms of accuracy, it's totally competitive. But take a look at that last column. That's where things get really interesting.
Because that is the absolute game changer. Every single one of those other methods, they had to be completely retrained from scratch for every new dataset. CausalFM? Nope. It was trained just once on all that simulated data, and then they could just apply it directly to each new problem. And it got those top-tier results, instantly.
So let's zoom out for a second. What does a future with this kind of technology actually look like? Because this is way more than just a clever research paper. This is a signpost pointing to a completely new way of using data to make some of our most important decisions.
When you boil it down, the benefits are huge. First, it's super fast and flexible. You get answers in seconds. Second, it's built on a Bayesian framework, which is a fancy way of saying it knows what it doesn't know. It can tell you how confident it is in an answer, and that is absolutely critical when the stakes are high. And maybe the biggest deal of all, this isn't just about one model. It's a general recipe, a blueprint for building a whole new generation of AI tools.
And this is really why this matters so much. Just imagine a doctor being able to instantly see the likely effect of a brand new treatment on a patient with a very specific profile. Or an economist who can, in seconds, model the ripple effects of a new policy. That's the kind of power, the kind of speed we're talking about here.
So it really leaves us with this one big, fascinating question. For years, we've been focused on AI that can predict what's next, and we're really only just scratching the surface there. But what happens? What new frontiers open up? What massive problems could we finally solve when we have an AI that truly understands why